when we deal with fairly simple molecules, we find that their behaviors are much easier to predict and explain. So here's a molecule on the left that I drew previously, not in a previous video, but before the video started. It's a nice simple molecule, 2-pentanone, and simulated the spectrum, and we get this picture right here. So that's the full view. You can see all the signals are isolated down to about the 1 to 2 ppm range. We can zoom in on these, just click and drag across the spectrum. And here's what we get. And when it comes to multiplicity, this structure follows these very simple multiplicity rules that we've already seen in other videos. So here we have a triplet on the end. This triplet corresponds to, let's hover over the signal and we'll see, oh, it corresponds to those 3 hydrogens. To be a triplet, those 3 hydrogens must have 2 neighbors, and they do. So here are 3 hydrogens, and those 3 hydrogens have 2 neighbors, and I'm going to hover over those 2 right now. So those 2 neighbors split these 3 hydrogens into a triplet. And furthermore, it's just not any triplet. It's a triplet that has the predicted intensity based on Pascal's triangle. So that has a 1 to 2 to 1 ratio, where the 2 side peaks are lower intensity and the middle peak is higher intensity, 1 to 2 to 1. Great. Okay, now let's look at these 2 hydrogens. Now, what is the multiplicity of that signal? It's a little bit messier. There are 6 lines, so that is it's a sextet. I think in this particular website it refers to as a hextet, but I think properly it's called a sextet. So it's a 6 signals, it's a sextet, and actually the signals there, if it's 6 signals, that must be from 5 neighbors. Well, these 2 hydrogens indeed have 5 neighbors. Has 3 hydrogens to the left and 2 more hydrogens, 3 hydrogens to the right, 2 more hydrogens to the left. That's 5 total neighbors. Now, if you're watching this, you might think, Dr. Stevens, it looks to me like those neighbors aren't exactly the same. There are 3 on one side, 2 on the other. They might be different. In simple molecules like this structure, while you're correct, they are different, they don't tend to behave differently. So this is a really simple multiplicity picture. You can't always make this assumption, but very often the assumption works, especially in simple molecules. So these 2 hydrogens have 5 neighbors. N equals 5, 5 plus 1, that gets us to the multiplicity of 6, and indeed we see this hextet with the predicted pattern that we'd see from Pascal's triangle. In this case, it would be 1 to 5 to 10 to 10 to 5 to 1. That's exactly what we see. And I won't belabor the point, but these 2 hydrogens have 2 neighbors next door, and because they have 2 neighbors, they show up as a triplet, 1 to 2 to 1. And of course, these 3 hydrogens by themselves, they don't have any vicinal neighbors. They show up as a singlet, as 1. So in our simple molecules, these basic simple multiplicity rules can be applied, and they're observed to work actually fairly well. So in the next video, we'll look at how we'll get into a little bit more detail about what these splitting patterns are and the idea of coupling constants.